Hey guys, this video is going to be about calculating equilibrium concentrations. It's the fourth video in the equilibrium series, and it is probably the most complicated, so make sure you're keeping up with what I'm talking about while I'm also writing on the screen. Most of it is going to all be calculations. It's the best way to learn this, so we're just going to get started with an example. Alright, so when you're calculating equilibrium concentrations, the typical problem involves finding the concentrations of the reactants and the products at equilibrium. This can become mathematically complicated, and sometimes you have to use the quadratic formula or find other avenues of solving for x. So really pay attention to what's given to you so that you know what you have to do at the time. So I'm going to try to point that out as I go through this to try to make it easier for you, but it can be difficult at first. All right, so with this example, we have this reaction right here. And it says at a particular temperature, the Kp for the reaction is 0.133. So we're given the Kp. And it says at equilibrium, the pressure of N2O4 was found to be 2.71. So the pressure of N2O4 at equilibrium is equal to 2.71 atm. And we want to know what the equilibrium pressure of NO2 is. So we want to know what the equilibrium pressure of NO2 is. All right. Well, I know that Kp expressions only have equilibrium values. So Kc is only made from molarities at equilibrium, and Kp's are only made from pressures at equilibrium. And since I have this at equilibrium, and I look at my equilibrium expression, my Kp is made from the pressure of NO2 squared divided by the pressure of N2O4. And I have this at equilibrium. And so I can find this at equilibrium because I have this one too, right? I have the Kp. So if I plug everything into my equilibrium expression, I have 0.133 is equal to the pressure of NO2 squared divided by 2.71. So to solve for the pressure of NO2, I'm going to multiply both sides by 2.71. That gets rid of this, and I get 0.36043 is equal to the pressure of NO2 squared. Then I have to take square root of both sides to get rid of that square. And my answer ends up being 0.6, and the units are atm. Before we go to the next problem, we're going to look at something called a Rice table. All right. And so if we want to find equilibrium concentrations, but we're only given initial concentrations, right? Because remember, the K's are using equilibrium concentrations. So initial concentrations do not always tell us what the equilibrium concentrations are going to be. So if we're given initial and we want equilibrium values, we have to use a Rice table. And the R in Rice stands for reaction, so we write the reaction. I stands for initial concentrations. C stands for change. Okay, so it's how the initial concentrations change before they get to finally the equilibrium concentrations. And the equilibrium concentrations are the ones that are in K, or equilibrium pressures, whichever is in there. Okay, now one thing you have to remember with change is that if you have a reaction, okay, if A is losing concentration, B has to gain concentration, because if it's going from A to B, if it's not over here anymore, it has to be over here. It's conservation of mass. All right, and the same thing is true if B is going down, then A has to be going up. That means the reaction is going that direction. Okay, so we have to pay attention to those things. All right, so this first example is a pretty easy example. We're given a reaction right here, and it says that this reaction is happening at 1325 Kelvin, and we have an initial pressure of 1 atm. So, and that's of S8. So I have an initial pressure of S8 equal to 1 atm. and it decomposes into S2. And at equilibrium, the partial pressure of S8 is 0.25. And we have to find Kp. So we want to find Kp. So I'm given initials, and I need to know equilibrium values in order to calculate Kp. So I have to use a Rice table. Okay, so Rice stands for reaction, so I'm going to write the reaction down first. And then I have I for initial, C for change, and E for equilibrium. So my initial that I know of is 1 atm of this, right? I have 1 atm of S8, and I don't have any of this. If I did, they would have to state that I did. So because it's not there, that means I don't have any of it. All right, and so this reaction must go forward. It can't go backwards because I don't have any of the product in order to go backwards, right? It can't go in this direction. There's none of this to make S8. Okay. Okay, so then that means the change that I'm going to see, I'm going to lose reactant and gain product. Now I'm given another piece of information. I'm given this, and it says the equilibrium pressure of S8 is 0.25. So that means I have 0.25 here, right? And I need to know my equilibrium values in order to calculate Kp. So my change, what happened as it went from 1 to 0.25? Well, it lost negative 0.75 was the change in order to get to 0.25. So that means on the other side over here, it has to gain not 0.75, but 4 times that amount. And the reason it has to gain 4 times that amount is because over here there's 1. And for every one that's lost on this side, 4 of these have to be gained. Well, I didn't lose 1, I lost 0.75. So I have to gain 0.75 times 4, which is going to be 3. So that means that this is going to be 3, because if I start at 0 and I add 3, I get 3. Okay, so now I can find my Kp. It's going to be 3 to the 4th divided by 0.25. And so my answer is 324. All right, I'm given a reaction, and I didn't type it out. I don't know why not, but I didn't. I have carbon monoxide, which is a gas, reacts with steam, which is a gas, to produce carbon dioxide gas and hydrogen gas. Okay, and it says at 700 the equilibrium constant is 5.10, so K is equal to 5.10, and it says calculate the equilibrium concentrations of all species if 1 mole of each component is mixed in a 1 liter flask. So what that tells me is that every single one of these up here is starting out with 1 mole per liter, right? So that means that the concentration of carbon monoxide will be equal to the concentration of H2O, will be equal to the concentration of CO2, will be equal to the concentration of H2, and all of these will be initial concentrations, and it will be 1 mole per liter. So 1 molar. All right, so all of those are initial, and I have to find equilibrium. So I have initial, and we want to find equilibrium values. So if we have initial and we want to find equilibrium values, we have to use Rice tables. I've got R reaction, I initial, C change, E equilibrium. So my reaction, carbon monoxide plus H2O, CO2, and H2. And my initial concentrations are all going to be 1 molar. All right, so that's all that I know, and I have to find my equilibrium values. And then I also know the only other piece of information that I know that I can get out of this is that my K, that's equal to 5.10, will be equal to the equilibrium concentration of H2 times the equilibrium concentration of CO2 divided by the equilibrium concentration of H2O times the equilibrium concentration of carbon monoxide. So I have this. I have these two things and that's it. All right, so then to fill in the information, first I need to ask which direction will this reaction go? Will I gain product or will I gain reactant? Well, if you're wanting to know which direction a reaction goes, we always look for Q, the reaction quotient. And so Q is equal to 1 times 1 divided by 1 times 1, which is 1. And so since Q is less than 5.10, is less than K, the reaction is going to go forward. So I'm going to be making product and using reactant. So then that means that this is going to be going down by a certain amount, and these are going to be going up by a certain amount. So this will be 1 minus x, this will be 1 minus x, this will be 1 plus x, and this will be 1 plus x. So then I can take these values here and plug them in to my equilibrium expression, and then I can solve for x. So I'm going to have 5.10 is equal to 1 plus x times 1 plus x divided by 1 minus x times 1 minus x. So then what I basically have is I have 1 plus x squared over 1 minus x squared. So I'm going to rewrite that. And then I have to take the square root of both sides to get rid of the squares. So the square root of 5.10 is 2.26. And then I have to multiply both sides by 1 minus x. So then I have I guess I should, you have to distribute here. 2.26 minus 2.26x is equal to 1 plus x. We're going to add 2.26 to both sides. And then subtract the 1. Divide both sides by 3.26. And so my x ends up being 0.387. Okay, we're almost done. And that's usually where students make the mistake, is they stop there. They're used to solving for x, so once they get x, they stop. But that's not the answer here, because the equilibrium value of carbon monoxide and water vapor is 1 minus x. So we have to subtract 1 minus the 0.387 value, right? The x value. And so carbon monoxide and water at equilibrium is going to be 0.613 each. And that's just taking 1 minus the x value of 0.387 that we just found for each of those. And then at equilibrium, carbon dioxide and hydrogen gas, we're going to add the 0.387 to 1, so you're going to get 1.387. And so those are the values there. All right, let's try another one. So I have the reaction given to me here, and we want to calculate the concentration of all species in equilibrium at equilibrium if we have 1 mole of pure hypochlorous acid in a 2-liter flask. So I have this is initial because I'm placing it in the flask. So I have initial and I want equilibrium. So that means I have to use a rice table. Rice, reaction, initial, change, equilibrium. My reaction, water plus Cl2O goes to Haeckel. And I also know that at K is going to be equal to the concentration of Haeckel squared over Cl2O times H2O. And that will be equal to 0.090. So then I have my 1 mole. This is initial concentration is going to be 1 mole in 2 liters. And so that's going to be 0.5 molarity. So I'm going to put 0.5 initially here. And I don't have any of this or any of this. Okay, so this time the reaction has to go this way because I don't have any reactant to go forward. I know that this is going to lose, and it's going to lose 2x because I have 2 of these. And this is going to go up by 1x. So at equilibrium, I will have 0.5 minus 2x, whatever 2x happens to be. And then for Cl2O and water vapor, I started with 0. I added x amount, so this is just going to be x, 0 plus x, and that is just going to be x. And so then I can take my equilibrium concentrations and I can plug them into my K. I'm going to have 0.5 minus 2x squared divided by x times x is equal to 0.090. So that's the same thing as 0.5 minus 2x squared over x squared. So then I'm going to take the square root of both of these, and I'm going to come up here. So the squares go away on that, and then 0.3, and multiply both sides by x. Add 2x to both sides, and then divide by 2.3. So my x is equal to 0.217. And so those are going to be my water and Cl2O concentrations at equilibrium. And then for HCl or hypochlorous acid, the concentration of that at equilibrium is going to be 0.5 minus 2 times x, which was the 0.217, and that is 0.066 molar. Now I will tell you a good check, if you get a negative number, that is not right. You can't have a negative concentration. You can have a negative change in concentration, but you cannot have a negative concentration. All right, now this one is probably a little harder to do, especially for those of you just in Algebra 2, but it's not impossible. I've seen some kids really master this. All right, assume gaseous hydrogen iodide is synthesized from hydrogen gas and iodine vapor. So we have H2 gas plus I2 gas goes to 2HI, and the Kp is 100, right? 1 times 10 squared is 100. So the Kp for this is equal to 100. And it says we have HI at 0.5, H2 at 0.01, and I2 at 0.005 atm, and it's mixed in a 5-liter flask. Calculate the equilibrium pressures of all species. Now, one thing that you have to watch out for that you cannot do is divide your pressure by volume to find some weird mixture of molarity and pressure. Guys, it's given, a Kp is given to us, so all these are good. You don't have to do anything to it. You don't have to divide it by this. It's irrelevant. It doesn't matter. Not for the problem that we have anyways. All of these are initial because it says suppose they're mixed in the flask together. So all of these are initial because they're mixed in the flask together, and we want to find equilibrium. So we have initial and we want equilibrium. So that means we have to do a Rice table. So my reaction, H2 plus I2 to HI, and initially I have a lot. HI is at 0.5. H2 is at 0.01, and I2 is at 0.005. And you can put it in there in scientific notation. It takes up less room to write it like this for these values. Now, if they were really, really small, it wouldn't. So now I need to know which way is it going to go. Is it going to go toward the product, or is it going to go to the reactants? Well, and the only way to find that is to look at Q. So real quick, Q is going to be 0.5 squared divided by 0.01 times 0.005, and if I calculate that, my Q is 5,000. And so since Q is greater than K, the reaction is going to shift back toward the reactant so that it can get smaller. So I'm going to lose product and gain reactant. So that means I'm going to lose negative 2x here because I've got 2 of them, and then I'm going to gain plus x and plus x on this side. So then I end up with 0.5 minus 2x, 0.005 plus x, and 0.01 plus x. So I can take these values then and plug them into an equilibrium expression that I haven't written yet. So my equilibrium expression, just in general, Kp is going to be equal to Hi squared divided by H2 times I2. So I'm going to plug those into that, and I'm going to write it up here at the top. So I have 100 is equal to, that's my Kp, 0.5 minus 2x squared divided by 0.01 plus x times 0.005 plus x. All right, so there's no way to take the square root of both sides here and fix this. We have to FOIL all this out. So if I do that, what I end up getting on the top, so I have 0.5 minus 2x times 0.5 minus 2x, and I'm going to FOIL it out. And I end up getting 4x squared minus 2x plus 0.25. And then I'm going to FOIL out this bottom too, right? Like that, and then like that, and then collect like terms. And I end up getting 5 times 10 to the negative fifth plus 0.015 x plus x squared. So now I have to multiply both sides by the denominator so that I can get rid of it over here and do the same thing. Okay, and I'm going to distribute this 100 because this is being multiplied by 100. I'm going to distribute the 100 to each value, right, and rewrite it so you can actually read it. So I get 0.005 plus 1.5x plus 100x squared is equal to 4x squared minus 2x plus 0.2. And then we collect like terms. So I'm going to move everything over here. So all this goes to 0. All right, and then you can use the quadratic equation if you feel like you have to do it that way. I will show you how to program a quadratic solver into your calculator, into the TI-84s or 83. You can also use a quadratic solver on your computer. So this is the A value, the B value, the C value. Don't forget the negative sign for C. Remember, it's if you want to do it on paper, negative b plus or minus the square root of b squared minus 4ac all over 2a, you can use that too. But I plug this into a quadratic solver on my calculator, and I end up getting two values for x, right, because of the plus or minus. So you get 0.03548, or you get negative 0.07194. Okay, so if I were to use this value, I would end up getting a negative value for this and this one. And you can't have a negative concentration, so I know that this is not valid. So this is my x value. So I'm going to use that to calculate my concentrations. And so if I plug that back in for H2, pressure of H2 at equilibrium is going to be equal to 0.01 plus 0.0355. So I end up getting 0.0455. And then my pressure for I2 at equilibrium will be equal to 0.005 plus 0.0355. And this, so that's going to be 0.0405 atm. And then my pressure for HI is going to be 0.5 minus 2x, and that's going to be equal to 0.429. And that's about as hard as these will get. I don't like to give you quadratic equations on the test, but I can't promise you won't have one or two on classwork assignments. I don't think they'll give it to you on the AP test. There's other ways you can do these and make sure that students understand the chemistry without having to use something where there's so many easy mistakes to be made. And then this is the last one, and the only reason I put this on here is I really, really, really like this problem a whole lot. Okay, so the Kp is 2.9 times 10 to the negative third, and I have this crazy wacky reaction, and it's in an experiment at 25 degrees Celsius, and we put a certain amount of this in there. And it's in a rigid container. That means it doesn't expand. It's not like a balloon. It's stuck at the volume that it's at. And so if gas builds up in there, the pressure is going to change. And we want to know what the total pressure is at equilibrium, which means we have to know the pressures at equilibrium. And it doesn't tell us how much of anything that we start with, but if I look at this, I know I have to find pressures at equilibrium on a given case, so I'm probably going to have to do a Rice table. So I'm going to go ahead and write that out. And so I'm going to write this in here, and I put that it's a solid. And usually in my Rice tables, I don't put stuff there if I don't put the phases there if I know they go in the K. But if they don't go in the K, then I'll put the phase there to remind me that they don't belong there, right? Because solids don't affect equilibrium at all. So all of this doesn't matter at all. All I know is that I'm not starting out with any of this. So that's 0. And I know that it has to increase. It has to go up because it can't go negative. So this is going to be plus 2x, and this is going to be x. So at equilibrium, this will be 2x, and this will be x. And then my Kp expression is simply going to be the pressure of NH3 squared times the pressure of CO2. So if I take my equilibrium values and I plug them into here, I should be able to get my pressures for those two products. So that's my Kp value from right here. And it's going to be equal to the pressure of NH3 at equilibrium, which is 2x. So 2x, and that has to be squared. And then CO2 is x, and it's not raised to anything. So if I square 2x, I have to square everything inside of this parentheses. So that's going to be 4x squared times x is equal to 2.9 times 10 to the negative third. And 4x squared times x is going to be 4x cubed. So then to solve for this, I have to undo the multiplication first. And then I have to raise both sides to the 1/3, or take the cubed root. That gets rid of that 3. And you can just put that in your calculator, raised to the 1 divided by 3. And my x is 0.0898 atm. That's x. So that is the pressure of CO2 at equilibrium. And then the pressure of NH3 at equilibrium is going to be twice as much. So that's 0.1797. Now, it asks us what's the total pressure. And so if you remember way back in your first chemistry class, the total pressure is always going to be all of the partial pressures added together. So the total, since these are the only two gases in the container, the total pressure is going to be equal to the partial pressure of carbon dioxide plus the partial pressure of NH3. And so that's going to equal, we're going to add these two numbers right here together, and that will be equal to 0.2695. So that's the answer. All right, that's it. Good luck.